Right now, as you read these words, a tiny aluminum spacecraft the size of a school bus is 163.4 astronomical units away from Earth. That is 24.4 billion kilometers, or 15.17 billion miles. To reach it with light, the fastest thing in the universe, takes 22 hours, 58 minutes, and 46 seconds, one way. The Sun, from Voyager 1's point of view, is no longer a blazing disk. It is just the brightest star in an ocean of stars, shining at magnitude -17, roughly 400 times fainter than we see it from Earth. Yet every single day, at exactly the scheduled time, a whisper of radio energy no stronger than 22 watts leaves that spacecraft, travels across the Gulf for nearly an entire Earth day, and lands perfectly inside a 70-metre parabolic dish in California, Spain, or Australia. When that signal arrives, it is weaker than the cosmic microwave background itself, about 10 to the -19th watts, or 1/10 billionth of a billionth of a watt. To give you scale, if you took a single AA battery and spread its entire lifetime energy evenly over the surface of Earth, the power falling on 1 square metre would still be 1 trillion times stronger than what Voyager 1 is sending us right now. Voyager 1 is moving away from the Sun at 16.98 kilometers per second, or 61,200 kilometers per hour. That is 3.58 astronomical units per year. Every second, it adds another 17 kilometers to the record of the farthest human artifact. Its twin, Voyager 2, is 136 astronomical units away and receding at 15.34 kilometers per second, slightly slower because it performed extra gravity assists at Uranus and Neptune. Between them, they have travelled a combined distance of more than 300 astronomical units, which is 45 billion kilometers. If you laid that distance end to end in a straight line of dollar bills, you could wrap the entire circumference of the Earth 1,200 times. The spacecraft were launched when Jimmy Carter was president, when the most powerful computer on Earth had less memory than a modern toaster. Their 8-track digital tape recorders hold 67 kilobytes total, less than one low-resolution photo on your phone. Their central computers run at 81,000 instructions per second. An Apple Watch today is roughly 100,000 times faster. Yet these two 825-kilogram probes have outlived every supercomputer of their era, every space shuttle, every human who signed their launch papers. They have survived 47 years of cosmic ray bombardment that would destroy modern electronics in weeks. They have crossed a region where the solar magnetic field flips direction 11 times per second, where the plasma density drops by a factor of 100 in a single day, and where the temperature of the ions is 30,000 to 50,000 Kelvin, even though the neutral gas around them is only 6,000 Kelvin. They are the only machines humanity has ever built that are truly outside the sun's domain, swimming in the ancient wind that blows between the stars. And they are still talking. Every 48 hours, mission engineers at JPL send up a command sequence that takes 46 hours to go out and back. They call it the longest round-trip conversation in history. The spacecraft answers with a carrier tone first, a pure sine wave that says, "I'm still alive." Then, a few minutes later, the science data trickles in at 160 bits per second, slower than the dial-up modems of the 1980s. That 160 basis points is enough to send one low-resolution plasma wave spectrum every 6 hours. Enough to tell us that the interstellar magnetic field is 0.5 nanotesla strong and tilted 37 degrees from the plane of the galaxy. It is enough to tell us that galactic cosmic rays above 200 megaelectron volts are 60% more intense outside the heliosphere than inside. It is enough to prove once and for all that the sun's protective bubble is real, finite, and astonishingly small compared to the true size of the solar system. We are listening to the voice of a machine that left Earth before the internet existed, before the first mobile phone, before the first CD. It is the longest continuously operating scientific experiment in human history, and it is being conducted from a place where no human being will ever stand. In the summer of 1977, the outer solar system opened its doors for for the first and possibly last time in our lifetimes. Jupiter, Saturn, Uranus, and Neptune had drifted into a rare geometric alignment that had not occurred since 1801 and will not repeat until 2159. From Earth's perspective, all 4 giant planets were lined up on the same side of the Sun, within a 47-degree arc, an angle narrower than the width of your fist held at arm's length. That alignment created a gravity-assist superhighway, a chain of invisible slingshots that could hurl a spacecraft from one planet to the next, adding tens of thousands of kilometers per second with 0 extra fuel. The mathematics is brutal and beautiful. Each gravity assist works by stealing a tiny fraction of a planet's orbital momentum. Jupiter alone orbits the Sun at 13.07 kilometers per second and has a mass 317.8 times that of Earth. When a spacecraft whips around it at the correct angle, it can pick up as much as 15 kilometers per second in a single pass. Do it twice, once at Jupiter and once at Saturn, and you leave the inner solar system faster than anything humanity has ever built before or since. Voyager 2 launched first on August 20th, 1977, atop a Titan IIe Centaur rocket. 16 days later, on September 5th, Voyager 1 followed on an identical rocket, but on a shorter, faster trajectory. Both weighed 825.5 kilograms at launch, including 105 kilograms of scientific instruments and 72 kilograms of hydrazine for attitude control. The key difference was the flight path. Voyager 1 was aimed to fly by Jupiter and then Saturn's moon Titan, a detour that would fling it upward out of the ecliptic plane at 35 degrees, ending its planetary tour after Saturn. Voyager 2 was given the grander, riskier assignment. Jupiter to Saturn, to Uranus to Neptune, staying in the plane of the planets the entire way. The speed gains were staggering. At Jupiter in March 1979, Voyager 1 arrived moving 10 kilometers per second relative to the planet and left moving 25 kilometers per second relative to the Sun. At Saturn, in November 1980, it arrived at 16 kilometers per second relative and departed at over 35 kilometers per second. Heliocentric, becoming the fastest human object ever recorded until the Parker Solar Probe's later dives. Voyager 2, after identical boosts at Jupiter and Saturn, continued on and received another 6 kilometers per second at Uranus in 1986 and another 5 kilometers per second at Neptune in 1989. Its final heliocentric escape speed settled at 15.34 kilometers per second, while Voyager 1's steeper trajectory gave it 16.98 kilometers per second. That 1.64 kilometers per second difference is why, despite launching second and later, Voyager 1 is now 27 astronomical units ahead and pulling away by 5.6 million kilometers every year. These numbers are not theoretical, they are etched into the actual trajectories. Voyager 1's current velocity vector is 16.982 kilometers per second at an ecliptic inclination of plus 35.4 degrees, pointing almost exactly toward the constellation Ophiuchus. Voyager 2's is 15.341 kilometers per second at minus 47.2 degrees inclination, heading toward the border of Parvo and Telescopium. In other words, one is flying above the solar system, the other below, and they will never see each other again. The alignment that made this possible was a 1-in-1, 176-year jackpot. The orbital periods are Jupiter 11.86 years, Saturn 29.46, Uranus 84.01, Neptune 164.79. For all 4 to cluster within 47 degrees again requires a resonance chain that only repeats every 177 years, on average. NASA's Voyager team knew they had one shot. Miss the launch window by even a few weeks, and the geometry would collapse. The spacecraft would arrive at Saturn too early or too late, and miss the Uranus-Neptune leg entirely. The launch windows were measured in days, not months. Voyager 2 had to lift off between August 20th and September 4th, 1977. Voyager 1's faster path had an even narrower window, September 1st to 10th. They hit both within hours of optimum. That gravity chain turned 1,600 kilograms of rocket fuel into a permanent escape velocity from the Sun. No chemical rocket ever built could have done it alone. Even today's most powerful upper stage, the Centaur V on Vulcan, would need 30 tons of propellant to push Voyager to the same speed in a single burn. The 4 planets did it for free, using momentum they borrowed from the Sun itself over billions of years. The result? 2 spacecraft that left Earth moving slower than the space shuttle are now the 3rd and 4th fastest objects humanity has ever launched, behind only Parker Solar Probe and the New Horizons plutonium counterweight that was jettisoned at 45 kilometers per second. They are faster than every comet, every asteroid, every Kuiper Belt object we have ever measured. They are true interstellar travellers, not because we gave them the speed, but because the giant planets handed it over like passing a baton in the longest relay race in history. And the door closed behind them. The next alignment in 2015-90 will be weaker, with a wider angular spread. And the door closed behind them. The next alignment in 2159 will be weaker, with a wider angular spread. By then our plutonium-238 stockpile will be nearly depleted, and no currently planned spacecraft will be ready to exploit it. The Voyager gravity highway is gone for the rest of the 21st century, and most of the 22nd. We caught the only train, March 5th, 1979. Voyager 1 dives into the Jovian system at 39 kilometers per second relative to the planet. In the span of just 48 hours, it returns more data than all previous missions to Jupiter combined. First comes the Great Red Spot. The images resolve it into a counterclockwise hurricane 3 times wider than Earth, with wind speeds clocked at 680 kilometers per hour at the periphery. The storm's clouds tower 8 kilometers above the surrounding deck, and its colour, salmon pink to brick red, comes from dredged up phosphorus and sulfur compounds cooked by ultraviolet light. Then comes the discovery that rewrote planetary science. Io. Voyager 1's cameras catch 9 active volcanic plumes shooting out of Io's surface in real time. The largest, from a volcano later named Loki Patera, rises 300 kilometers high, higher than the International Space Station orbits Earth, and is moving at 1 kilometer per second. The surface itself is painted in yellows, oranges and blacks, with 0 impact craters. Io is the most volcanically active body in the solar system, resurfaced entirely every million years by 0.1 to 1 meter of fresh lava per year. The energy source? Tidal heating. Io is locked in a 1 to 2 to 4 orbital resonance with Europa and Ganymede, and Jupiter's gravity kneads its interior like dough, generating 100 times more heat per square meter than Earth receives from the Sun. Voyager measured the heat flux at 2.5 watts per square meter. Earth's geothermal output is only 0.08 watts per meter squared. Next, the faint rings. Everyone expected Saturn to own the only ring system. Voyager 1 finds Jupiter has one too, a gossamer veil of dust knocked off the 4 small inner moons, Metis, Adrastea, Amalthea, Thebe. The main ring's only 30 kilometers thick, but stretches 6,000 kilometers outward from the cloud tops, glowing faintly in forward scattered light. November 12th, 1980. Voyager 1 reaches Saturn. The rings resolve into thousands of individual ringlets, some braided, some kinked, some propagating density waves like ripples in a pond. The spacecraft flies through the plane at a distance of only 3,000 kilometers above the cloud tops, closer than Los Angeles to New York. It discovers shepherd moons, Prometheus and Pandora, orbiting just inside and outside the narrow F ring, keeping it confined to a ribbon only 100 kilometers wide. by gravitational nudges every 15 hours. Then Titan, the largest moon in the solar system, 5,150 kilometers across, bigger than Mercury, disappears completely behind an opaque orange haze. Voyager's instruments measure surface pressure at 1.5 bars, 50% denser than Earth's, and temperature at minus 179 degrees Celsius. The atmosphere is 98.4% nitrogen, 1.6% methane, with trace ethane, propane, acetylene, and hydrogen cyanide. Photochemistry in the upper atmosphere builds complex hydrocarbons that rain out as tar-like droplets, forming lakes and seas we wouldn't confirm until Cassini 25 years later. Titan's surface is hidden, but Voyager's radio occultation experiment proves it has a thick atmosphere and gives us the first accurate radius, 2,575 kilometers. Voyager 1's cameras are turned off forever on February 14th, 1990, after the famous family portrait. Earth has a pale blue dot in a scattered sunbeam. But Voyager 2 is still going. On January 24th, 1986, Uranus. The planet is tipped 98 degrees on its side, rotating like a barrel rolling down a hill. Its magnetic field is tilted 59 degrees from the spin axis and offset by 0.3 planetary radii, creating the most lopsided magnetosphere in the solar system. Voyager 2 discovers 10 new moons and a set of dark, narrow rings, only 10 to 100 kilometers wide, made of carbon-rich material darker than coal. The rings show clear signs of gravitational resonances with small moons. Cordelia and Ophelia shepherd the Epsilon ring exactly the way Prometheus and Pandora do Saturn's F ring. Atmospheric winds reach 900 kilometers per hour, despite the planet receiving only 1/40th the sunlight Earth does. Methane in the upper atmosphere absorbs red light and scatters blue, giving Uranus its featureless cyan colour. August 25th, 1989. Neptune, the last planetary encounter. Voyager 2 approaches a world that should be dead calm, only 1/900th Earth's insolation. Yet it finds the fastest winds in the solar system, 2,100 kilometers per hour, near the equator, supersonic relative to the planet's sound speed. The Great Dark Spot, an anticyclonic storm the size of Earth, rotates every 16 days and casts shadows on the cloud deck 50 kilometers below. Triton, Neptune's largest moon, steals the show. It is 2,700 kilometers across and has a surface temperature of minus 235 degrees Celsius, the coldest measured in the solar system, and sports active nitrogen geysers shooting 8 kilometers into the sky, leaving dark streaks hundreds of kilometers long. Retrograde orbit, cantaloupe terrain fractures, and a density of 2.06 grams per cubic centimetre prove Triton is a captured Kuiper Belt object, probably stolen from a binary companion billions of years ago. In total, the two Voyagers discovered 26 new moons, 5 new ring systems, 3 new atmospheres thick enough to hide surfaces, Io, Titan, Triton, and the first active volcanism beyond Earth. They measured magnetic fields at 4 giant planets, found lightning on Jupiter, Saturn, Uranus and Neptune, and gave us the first close-up proof that planets are not static museum pieces, but violently active worlds. Every one of those discoveries came from cameras with only 800 by 800 pixel resolution, spectrometers that scanned one line at a time, and computers with 4K of usable memory. The raw images were transmitted at 44.8 kilobits per second at Jupiter, dropping to 600 bits per second by Neptune, slower than a 1990s fax machine. Yet the data volume was so vast that NASA needed 4 years after the Neptune flyby just to process everything. On August 25, 2012, at 11:03 UTC, Voyager 1 did something no machine had ever done before. It crossed the heliopause, the precise boundary where the solar wind finally loses its centuries-long battle against the pressure of the interstellar medium. The crossing was not gradual. It was a knife-edge event that lasted less than one Earth day. The proof came from two instruments still alive after 35 years: the low-energy charged particle detector and the plasma science experiment. For decades, the plasma instrument on Voyager 1 had been blind. Its final frequency channel failed in 1992. But the backup plan worked perfectly. The plasma wave subsystem, originally designed to listen for lightning on Jupiter, suddenly detected a screaming tone at 2.6 kHz, the unmistakable signature of electron plasma oscillations, excited by a solar shockwave that had propagated all the way from the Sun in early 2012. The density jump was brutal, from 0.002 electrons per cubic centimetre inside the heliosheath to 0.08 electrons per cubic centimetre in interstellar space, a 40-fold increase in a single step. At the same moment, galactic cosmic rays, particles accelerated in supernova remnants millions of years ago, spiked permanently to 80 to 100 counts per second, while solar energetic particles above 70 million electron volts fell to near zero. The magnetic field strength doubled from 0.25 nanotesla to 0.50 nanotesla and rotated 37 degrees upward, aligning almost perfectly with the average direction measured by the Interstellar Boundary Explorer satellite, IBEX, from Earth orbit. Everything happened exactly as predicted by the best models, except the models were wrong about one thing. There was no clean bow shock, no neat bubble wall. Instead, the heliopause turned out to be a porous, frothy, magnetic foam layer 20 to 30 astronomical units thick, where solar and interstellar fields tangle like two smoke plumes colliding. Voyager 2 confirmed the picture 3 years later, crossing its own heliopause on November 5th, 2018, at a distance of 119.7 astronomical units. Voyager 1 was at 144 astronomical units by then. The geometry was different. Voyager 2 flew south of the ecliptic, into the compressed nose of the heliosphere, where the interstellar wind rams head-on into the Sun's outflow. Its plasma instrument was still working, so we got direct density and temperature measurements for the first time. Interstellar plasma temperature, 15,000 to 30,000 Kelvin. Flow speed relative to the Sun, 26.3 kilometers per second, coming from the direction of the constellations Scorpius and Ophiuchus, the same local interstellar cloud we live in. The heliosphere is therefore moving through the galaxy at roughly 23 to 28 kilometers per second, relative to the stars around us, creating a comet-like tail that stretches at least 400 astronomical units behind the Sun, possibly much farther. The size of the heliosphere is now known to within 10%. The distance to the heliopause in the Voyager 1 direction, the heliotail flank, is 121 to 130 in the nose direction, toward the constellation of Sagitta. It is compressed to about 90 to 100. In the tail, it stretches to at least 350 to 400 and possibly more than 1,000 astronomical units before finally dissolving into the galactic medium. That makes the entire heliosphere roughly 800 astronomical units in diameter along the direction of motion, smaller than the inner Oort cloud, which begins around 2,000 to 5,000 and extends to 100,000 astronomical units or more. In other words, the Sun's magnetic bubble is tiny on galactic scales, barely a speed bump in the interstellar wind. The shape is not a sphere. It is a blunt-nosed, elongated droplet with a squashed front and a long, bifurcated tail split by the solar magnetic field into northern and southern lobes. The heliopause itself is only about 1 to 2 astronomical units thick in places, thinner than the orbit of Mercury. Yet it is strong enough to deflect 70 to 90% of incoming galactic cosmic rays below 500 million electron volts, acting as a radiation shield for the entire planetary system. Without it, Earth's atmosphere would be stripped by cosmic rays at a rate 100 times higher than today. Both spacecraft are now measuring the pristine interstellar medium for the first time. The hydrogen to helium ratio is 12 to 1 by number, slightly higher helium than inside the heliosphere. The carbon to oxygen ratio is 0.75, confirming enrichment from ancient supernova explosions. The magnetic field is compressed and draped around the heliopause like fabric over a ball, creating a region of turbulent reconnection where magnetic energy is converted into particle acceleration. Voyager 1 has been surfing these reconnection waves since 2017, seeing sudden field reversals lasting only hours, proving the boundary is alive and breathing. We now know the heliosphere is one of millions of similar astrospheres around other stars. The nearest one, around Proxima Centauri, is only 4.37 light-years away. In about 300,000 years, Voyager 1 will drift through the Oort cloud of some unknown star and possibly feel the pressure change when it enters another star's domain. But for now, it is the first and only witness to the space between stars exactly as nature made it, untouched by any sun for billions of years. And it is still sending the data one bit at a time, across a distance that grows by 540 million kilometres every year. Picture this: a 3.7 metre aluminum dish, high gain, parabolic, gold-plated mesh, bolted to a 48-year-old spacecraft that is now colder than liquid nitrogen and moving away from us at nearly 61,200 kilometres per hour. That dish is currently pointed at Earth with an accuracy of better than 0.4 degrees, an angle so precise that if you scale the distance to the width of a human hair at arm's length, the beam would miss Earth entirely if it drifted by just 1 micron. Every second, that dish pours 22.4 watts of radio power, continuous wave, into a beam only 0.65 degrees wide at X-band, 8.4 gigahertz, and an even tighter 0.28 degrees at S-band, 2.3 gigahertz. 22 watts is less than the legal limit of a children's walkie-talkie in most countries. It is the same power as a compact fluorescent bulb from the early 2000s. From Earth, the Sun delivers about 1,366 watts per square metre at the top of the atmosphere. From Voyager 1's current distance, the Sun delivers only 0.0023 watts per square metre, meaning the spacecraft's own transmitter is now 10,000 times brighter than sunlight at its location. The signal spreads according to the inverse square law. By the time it has travelled 163.4 astronomical units, the power flux on Earth is 1.8 times 10 to the negative 26th watts per square metre. That is 0 followed by 25 zeros and 18 watts per square metre. To detect it, NASA uses the Deep Space Network's 370-metre antennas, Goldstone DSS-14, Madrid DSS-63, and Canberra DSS-43, plus the 34-metre high-efficiency dishes and the very large array when needed. The 70-metre dish has a collecting area of 3,850 square metres, so the total power actually captured is about 7 times 10 to the negative 23rd watts, roughly the energy of one single photon every 4 seconds at X-band. Yet we lock onto it perfectly every single day. The carrier is recovered with a phase-locked loop that can track frequency drifts as small as 0.003 Hz over a 23-hour light time delay. The spacecraft's hydrogen mesa reference oscillator has aged only 1 part in 10 to the 13th power per year, so the predicted Doppler shift is known to within centimetres per second. Engineers send commands at 7.2 watts from the 70-metre dishes, upgraded to 20 kilowatts for brief periods when absolutely necessary. And even then the signal arrives at Voyager carrying only 10 to the minus 18 watts. meaning the spacecraft's receiver detects roughly 1 photon every 2 seconds and still decodes the command perfectly. Current round-trip light time for Voyager 1 is 45 hours, 57 minutes, and 32 seconds. For Voyager 2, it is 38 hours, 8 minutes. Every command is a 46-hour gamble. You send it wait almost 2 full days, and only then do you know whether the spacecraft understood and executed it. In October 2024, engineers sent a command to Voyager 1 to switch to a backup thruster branch that hadn't been used since 1980. 46 hours later, the carrier tone shifted exactly 0.013 Hz as predicted, confirming the switch worked. That is engineering across 24.4 billion kilometers with 1970s hardware. The link budget is now so tight that every decibel counts. The spacecraft uses convolutional coding with constraint length 7 and rate 1/2, giving 5.2 decibels of coding gain. The ground stations cool their MESA amplifiers to 4 Kelvin with closed-cycle helium refrigerators, squeezing another 2 decibels of noise performance. When the signal is weakest, they array multiple antennas together. Goldstone 70 meters plus Canberra 70 meters plus 234-meter dishes can add another 6 decibels. In 2023, they tested linking the DSN with the Very Large Baseline Array's 27 dishes across the US, achieving a temporary 9 decibel boost. That single trick bought us roughly 3 extra years of science. Bit rates have been stepped down over the decades. At Jupiter, they were 115,200 bits per second. At Neptune, 600 BPs. Today, the engineering telemetry comes in at 160 BPs, science at 40 BPs on the best days. The plasma wave instrument, our most important remaining dataset, returns 148-second spectrum every 192 seconds, containing 256 frequency channels from 10 Hz to 56 kHz. That single spectrum, just 4 kilobits, takes 100 seconds to transmit. In that time, Voyager 1 travels 1,700 kilometers farther into interstellar space. Inside each Voyager sits a trio of multi-100-watt radioisotope, thermoelectric generators, MHWRTGs, the same design that flew on LES-8 and LES-9 military satellites in the 1970s. At launch, the 3 units together produced 474 watts of electrical power from exactly 13.06 kilograms of plutonium-238 dioxide. That plutonium was bred in the Savannah River reactors during the height of the Cold War, and it is the purest heat source humanity has ever launched. 99.997% Pu-238, almost no Pu-239 contamination. The decay chain is simple and relentless. Pu-238 arrow U, 234 plus alpha, 5.59 mega electron volts. Half-life equals 87.74 years. Specific power equals 0.567 watts thermal per gram. On September 5, 1977, every gram was delivering exactly that 0.567 watts. 47 years later, the radioactive atoms have decayed by 37.8%, so the remaining 8.12 kilograms of fuel now produce only 0.357 watts per gram. Total thermal output has fallen from 2,470 watts to 1,550 watts, a straight exponential curve with no surprises and no mercy. The conversion efficiency of the silicon-germanium thermocouples has also degraded. At launch, they turned 6.6% of the heat into electricity. Bombardment by cosmic rays and the slow sublimation of tellurium doping have dropped that to 5.8%. Combined, the two effects give us the observed power law. Electrical power today, October 2025, Voyager 1, 249.2 watts, Voyager 2, 253.1 watts. That is a loss of exactly 4.78 watts per year since 2012, when the decline stabilised after the last instrument heaters were turned off. NASA tracks it to the milliwatt. Every 6 months the power drops another 2.39 watts, like a clock you can set your calendar by. The shutdown sequence is already written and rehearsed. In 2026, turn off the cosmic ray subsystem, CRS, on both spacecraft saves 4.8 watts. In 2027, turn off the low-energy charged particle instrument, LECP, saves 3.9 watts. In 2028, switch from the X-band TWTA, 22 watts, to the S-band, 9 watts. Saves 13 watts instantly. 2029 to 2030, begin alternating science instruments in 90-day on-off cycles. 2031, final science instrument, plasma wave subsystem. Off, saves 2.7 watts. 2032 to 2035, engineering telemetry only at 40 BPs, then 10 BPs. 2036, last command uplink. Power drops below 180 watts to no more attitude control, to antenna drifts off Earth, to silence. After 2036, the RTGs will continue falling at 4.2 watts per year. By 2040, they will be below 160 watts. By 2050, they will be below 120 watts. By 2069, the original design lifetime of 92 years, they will be at 97 watts, just enough to keep the transmitter warm. The plutonium itself will still be 71% intact in the year 2010 and 44% in 2020. The plutonium itself will still be 71% intact in the year 2100 and 44% in 2200. The last watt of heat will not disappear until the year 2346, 569 years after launch. But long before that, around 2150, the thermocouples themselves will fail as the last tellurium atoms sublimate away and the silicon-germanium legs become insulators. The spacecraft will freeze solid at interstellar background temperature, 2.7 kelvins, and the remaining plutonium will simply sit there, quietly clicking out alpha particles for another 800 years, until even the ceramic fuel pellets crumble. NASA has already begun the rationing. In 2019, they fired up backup heaters that hadn't been used since Saturn to warm the fuel lines for a thruster switch. In 2024, they turned on a set of shunt radiator heaters for exactly 67 minutes to prevent the cosmic ray detector from freezing, then shut them off again. Every watt is now accounted for in a spreadsheet that projects the exact date each instrument must close off. The curve is merciless, but it is also beautiful in its purity, a perfect exponential decay that will outlast every nation, every language, and every corporation that existed when the plutonium was poured into its graphite casks in 1975. When the last human who ever heard Voyager's signal is long gone, the 3 RTGs will still be glowing at 50 watts, keeping a dead spacecraft warm in the dark between the stars for centuries more. That is the true measure of how far we reached. We did not just send a probe into interstellar space. We sent a tiny, dying star that will shine quietly for 600 years after every one of us is dust. If you want to know how alive Voyager really is in 2025, look at the last 12 months alone. 3 separate times, engineers have reached across 163 astronomical units and performed open-heart surgery on a machine that was already middle-aged when the Berlin Wall fell. In October 2023, Voyager 2 antenna drift crisis. On October 20th, the Canberra 70-metre dish noticed the carrier signal had dropped 38 decibels in a single pass, effectively disappearing. The spacecraft had accidentally fired its attitude control thrusters for 0.25 seconds too long during a routine calibration, nudging the high-gain antenna 1.95 degrees off Earthline. At 136 AU, that is a pointing error of 460 million kilometers, more than the distance from the Sun to Jupiter. The spacecraft was screaming into empty space. NASA had exactly one trick left: a pre-programmed autonomous fault protection routine written in 1977 that triggers every 203 days. It commands a full scan of the sky, looking for Earth's radio beacon using the low-gain antenna. On January 24, 2024, exactly 96 days after the mishap, the routine fired. Voyager 2 swept its beam across the ecliptic, locked onto Canberra's 18-kilowatt uplink at S-band, and repointed itself to within 0.12 degrees. 46 hours after the scan began, the signal jumped back to full strength. No human being lifted a finger during the recovery. The spacecraft saved itself exactly as the original programmers predicted it would half a century earlier. On April 2024, Voyager 1 memory corruption apocalypse. On April 19, 2024, Voyager 1 suddenly began transmitting pure gibberish on both the X-band and S-band downlinks, repeating blocks of alternating ones and zeros, no engineering data, no science, no attitude information. Diagnosis: a single bit flip in the flight data subsystem FDS memory, caused by a galactic cosmic ray strike, had corrupted the pointer table, forcing the computer to read instructions from a dead memory chip that was removed in 1980. Engineers had 22 hours of light time delay and only 160 bits per second to work with. Over the next 5 months, they performed the longest distance memory surgery in history. May 2024 sent a command to relocate 5 separate code segments into unused memory regions. In June, poked individual memory addresses one by one to find healthy RAM blocks. In July, rewrote the master pointer table by hand, 256 bytes at a time. In August, issued a single command that swapped the FDS to a backup memory bank last used in 1979. And on August 29, 1542 UTC, coherent engineering telemetry returned after 293 days of silence. The fix required transmitting 1,847 individual commands, each one taking 46 hours to confirm. The team worked 7 days a week for 5 straight months, sleeping under their desks at JPL. When the first readable frame finally arrived, the entire Deep Space Operations Center erupted in cheers loud enough to be heard in the next building. In November 2024, thruster residue crisis and the 5-year reprieve, both spacecraft have been using the same set of trajectory correction thrusters since 2017, when the primary attitude control branches began clogging with silicon dioxide residue from 47 years of hydrazine decomposition. By late 2024, Voyager 1's branch C thrusters were firing only 60% as long as commanded, and pressure readings showed the fuel lines were 82% blocked. Instead of switching to the last clean branch and burning 4 years of life in one go, the team rewrote the flight software in real time to implement pulse width stretching. Each thruster burn is now extended by 38% in duration, but reduced in frequency by 62%. The change drops the total number of firings from approximately 2,800 per year to approximately 900 per year, extending usable life from December 2025 to mid-2031, an extra 5.3 years bought with nothing more than a software patch sent at 16 bits per second. Temperature management has become an art form. In 2024 to 2025, they are running the spacecraft at negative 89 degrees Celsius on average, 30 degrees colder than design spec. The cosmic ray subsystem on Voyager 1 is now kept alive by cycling its heater on for only 11 minutes every 48 hours, using 0.37 watts average. The magnetometer boom on Voyager 2 is so cold that its thermal blanket has contracted 4 millimeters, but the sensor still reads the interstellar field to 0.01 nanotesla precision. They are also experimenting with power sharing between the two spacecraft indirectly. When Voyager 2 needs a high power command, like a thruster branch switch, they schedule it during a Canberra pass and simultaneously reduce Voyager 1's telemetry rate to 40 bits per second for 6 hours, freeing up ground station transmitter power to boost Voyager 2's uplink by 3 decibels. The two spacecraft have never been closer than 27 astronomical units to each other, yet they are cooperating like twins sharing a single oxygen tank. These are not routine operations. These are miracles performed daily by a team of 18 engineers who know every single bit of the 1977 code by heart. They have no spares, no second chances, and no margin. Every command is irreversible. Every watt is priceless. And yet, in the last 365 days alone, they have pulled Voyager back from the brink 3 separate times. This is not a spacecraft on life support. This is a 48-year-old marathon runner who just broke the world record for the 100-meter dash while carrying his own hospital bed. Sometime between late 2035 and mid-2036, depending on which RTG decays a little faster, the last surviving watt meter on Earth will drop below the red line marked minimum for transmitter plus gyro plus receiver. On that day, one of the 70-meter dishes will send the final command, a simple 37-bit sequence that tells the spacecraft to power down everything except the ultra-stable oscillator and the S-band exciter. 46 hours later, the carrier tone will weaken, stretch, and then for the first time since September 5th, 1977, go perfectly silent. No explosion, no drama. Just the quiet click of a relay opening in the dark, 26 billion kilometers away. After that, the two Voyagers become true interstellar relics. Dead hardware coasting forever at 17 and 15 kilometers per second, carrying the only evidence that intelligent life ever existed in this corner of the Orion Arm. First, the numbers of the endless journey. Voyager 1 is currently aimed at galactic coordinates, heading almost straight out of the galactic plane toward the North Galactic Pole. Its trajectory will never come closer than 1.6 light-years to any star for the next 300,000 years. The closest approach on record is to the red dwarf TYC 3135-513-1 in the constellation Camelopardalis in 302,459 AD, distance 1.61 light-years. After that, it drifts into the galactic halo, slowly climbing above the disk at 14 kilometers per second vertical velocity. In 1.4 million years, it will be 500 light-years above the plane, in a region where the stellar density is less than 1 star per 1,000 cubic light-years. By then, the Sun will have completed 5 full orbits around the galaxy and be unrecognizable in an entirely different spiral arm. Voyager 2 is aimed almost exactly opposite, plunging below the plane toward the southern constellations Parvo and Telescopium. Its closest recorded stellar encounter is with Ross 248, a red dwarf in Andromeda, in 40,276 AD at 1.75 light-years. After that, it crosses the galactic plane again in about 900,000 years and begins climbing into the southern halo on the far side of the galaxy. Both spacecraft will outlive Earth itself. In 5 billion years, when the Sun expands into a red giant and engulfs Mercury, Venus, and possibly Earth, The Voyagers will be 0.08 and 0.07 light-years out, still perfectly preserved at 2.7 Kelvin, still carrying their golden records. The records themselves are the part that keeps astronomers awake at night. Each is a 30-centimetre copper disc, electroplated with 99.96% pure gold, encased in an aluminium jacket with a uranium-238 coating on the outer edge, so that any future finder can measure the decay ratio and know exactly how old it is. Half-life 4.468 billion years. Playback instructions are etched on the cover in binary, along with a map of 14 pulses, accurate to 1 millionth second, giving the location of the Sun to within 1 light-year, even if the entire Milky Way has rotated 50 times. The audio content runs 1 hour 58 minutes and contains 115 analog encoded images, including calibration circle, DNA structure, human anatomy, and the UN building. 55 languages, including ancient Sumerian, Akkadian, and Hittite. It also contains whale song, Beethoven, Louis Armstrong, Chuck Berry's Johnny B. Good, traditional music from Peru, India, China, Japan, Azerbaijan, and New Guinea. And for natural sounds, thunder, rain, surf, birds, volcanoes, a human heartbeat, a kiss, and the sound of a mother comforting her child. The stylus and cartridge are pure sapphire and diamond mounted on the cover. In vacuum at 2.7 Kelvin with no oxidation or thermal cycling, the groove wear is effectively zero. Calculations show the record will remain playable for at least 1 billion years, possibly 2. The aluminum cover will erode by cosmic ray sputtering at about 0.1 ångstrom per year, meaning it will take 40 million years to lose 1 micron of thickness. The gold plating will last longer than the disk itself. In other words, long after every trace of human civilization has been burned away by the sun, 2 small golden messages will still be sailing perfectly preserved through the galaxy, carrying the sound of a woman saying hello in 55 ancient and modern tongues, and a rock and roll song from 1958 that will outlast the oceans. And they are not alone. The spacecraft themselves are time capsules of late 1970s technology, 8-track tape recorders, vacuum tube travelling wave amplifiers, wire-wrap circuit boards soldered by hand, and commands written in hexadecimal that still execute perfectly after half a century of radiation. Every solder joint, every capacitor, every relay is frozen in 1977. When some future probe finally intercepts one of them, tens or hundreds of millions of years from now, they will find a machine that looks brand new. Because at 2.7 Kelvin nothing corrodes, nothing ages, nothing moves. The final irony, the plutonium that powered them will still be warm. In the year 2500 AD, each RTG will still be producing roughly 40 watts of heat. In 30 AD, 25 watts. Even in the year 10,000 AD, the fuel pellets will be glowing at a few watts, keeping the spacecraft's core temperature a few degrees above the cosmic background for another 20,000 years. The last human voice on the golden record will fade long before the last spark inside the RTGs finally turns off. So yes, one day soon the whisper stops, but the journey does not. It simply becomes silent, eternal, and unstoppable. 2 small machines, each the size of a grand piano, will spend the next billion years crossing the galaxy like bullets fired from a gun that no longer exists, carrying the only proof that someone once looked up at the stars and said, "We were here. We were small and curious, and we were not afraid of the dark." Somewhere in the year 2036, the last engineer who ever sent a command to Voyager will close the control room door for the final time. The screens will go dark, the coffee cups will be thrown away, the building will eventually be demolished, or repurposed. The deep space network will be upgraded, dismantled, or abandoned. And none of it will matter, because out there, 28 billion kilometers away and still accelerating into the galaxy, 2 tiny spacecraft will keep flying straight and true, carrying the sound of thunder, the laughter of children, and the heartbeat of a species that reached farther than its own star. They will never slow down. They will never turn back. They will never be forgotten by the universe, even when every memory of them on Earth is gone. That is the real mission of Voyager. Not to explore the planets, not to cross the heliopause, not even to deliver a message to aliens. The real mission was to prove that curiosity is stronger than entropy, that courage can outrun time itself, and that a single generation of clever apes can build something that will outlast their star, their oceans, and their entire civilization.